All right, today we're going microscopic. We're diving deep into the world of 7 nanometer chips to solve a really fascinating mystery. These are the tiny engines that power our entire world. But there's a problem. Transistors that are designed to be perfectly identical, well, they aren't behaving that way. So let's get right into it and figure out what's going on. So here we are at section 1, a microscopic mystery. And our story really kicks off with this puzzle, one that has massive consequences for how well our chips perform. It's all about something called local layout effects, or LLEs for short. And the big idea here is pretty simple, actually. A transistor doesn't live in a vacuum. Its behavior isn't just about its own specs. It's about who its neighbors are. Which brings us to the big question, right? The one that's driving this whole investigation. Why do identical transistors misbehave? I mean, how is it possible that you can design 2 transistors to be exact copies of each other, put them on the very same piece of silicon, and yet they perform differently? It sounds kind of crazy, but the answer, as it turns out, is hiding in plain sight, or rather in the empty space between them. Okay, so let's break this down. Imagine you have transistor A. On its own, it works perfectly, right? Exactly as expected. But then you take its identical twin, transistor B, and you put it next to some other stuff on the chip. All of a sudden, its performance starts to vary. Now, the key thing to get here is that this isn't just some random glitch. Nope, this is a systematic, predictable problem, and it's a huge headache for chip designers. All right, section 2, the PMOS-NMOS divide. Now, this is where we get our first major clue. The breakthrough came when researchers looked at the 2 main types of transistors you find on a chip, PMOS and NMOS. And they didn't just look at a few. They looked at data from over 30,000 test devices. What they found was a massive difference in how these 2 types of transistors react to their surroundings. So get this, for PMOS transistors, the effect is just huge. We're talking a performance shift of more than 10%. Now, when we say performance, we're really talking about their drive current, basically how fast they can switch on and off. And in the world of high-performance chips, a 10% swing, that is absolutely massive. It's a game changer, and not in a good way. But then you look at the NMOS transistors, and yeah, they're affected too, but the shift is way smaller. It's less than 5%. So you've got this huge divide, right? PMOS transistors are super sensitive, while NMOS transistors are much more stable. The obvious question is, why? What makes them so different? And boom, this chart right here, this is basically the smoking gun. What you're seeing is the performance of thousands and thousands of transistors. Look at the blue lines. That's the NMOS. See how tightly they're clustered? It really doesn't matter if they have a neighbor or not. Their performance is super stable. But now look at the red lines for PMOS. Wow, that is a huge shift to the side. Just having a certain structure nearby pushes the entire performance curve over. You can literally see how much more sensitive PMOS is. Okay, section 3. Meet the layout saboteurs. So if the neighbors are the problem, we need to know who these troublemakers are. In the 7 nanometer technology, it really boils down to 2 main culprits, 2 structures that are basically sabotaging the performance of the transistors around them. So let's unmask our suspects. So suspect number 1 is something called a diffusion break, or DB. Now, its official job is pretty simple. It's an electrical insulator. It's there to stop current from leaking between different transistors. But it has a secret life. By physically cutting into the silicone, it also creates mechanical stress. And that stress completely changes the physics of any transistor sitting next to it. And our second suspect is the gate cut, or GC. See, when chips are made, the gates often start out as these long, continuous lines. Then they get cut up into individual pieces. And just like the diffusion break, this cut is supposed to be just for electrical isolation. But again, it does more than that. It messes with the mechanical stress that engineers have so carefully designed into the transistor in the first place. Now, here's a crucial piece of the puzzle. It's not just that these cuts exist, it's when they're made during the whole manufacturing process. And this particular 7 nanometer technology uses what's called a gate cut first process. Trust me, that little detail makes a huge difference in how all this stress stuff plays out. Gate cut first is exactly what it sounds like. The cut happens super early in the process, right after the main gate pattern is laid down. And importantly, it happens before a bunch of other high-stress layers and materials are added on top. Think of it like this. By cutting it early, you're leaving the ends of that gate exposed, making them way more sensitive to all the mechanical stress that gets piled on later. Okay, section 4, a tug of war of stress. So we've got our suspects, the diffusion break and the gate cut. Now we need a motive. Why do they mess with PMOS so much more than NMOS? The answer is all about the physics of mechanical stress. And in modern chips, stress isn't a bug, it's a feature. It's carefully engineered to boost performance. But it's a very delicate balancing act, kind of like a microscopic tug of war. And this is the absolute key to the whole mystery. For PMOS, it's simple. It loves one thing, being squeezed along the direction the current flows. That's called longitudinal compressive stress, and it makes PMOS transistors way faster. Simple, right? But for NMOS, it's the total opposite. That same squeezing actually hurts its performance. So for NMOS, you have this complex tug of war between stress in 3 different directions, and they all kind of fight each other, often canceling each other out. And you can see that tug of war perfectly in these charts. Look at the PMOS chart on the left. See that orange line? That's the longitudinal stress we were talking about. It's the only one that really matters. It completely dominates. Now look at the NMOS chart on the right. Whoa, it's a totally different picture. You've got 3 different forces all pulling and pushing against each other. And that is why the overall effect on NMOS is so much smaller and more complicated. And that brings us to our final section, silicon evidence meets simulation. This is the grand finale, the final piece of proof. We have a really solid theory about what's going on, but can we actually prove it? Well, this is where the rubber meets the road. You take the real-world measurements from actual silicon and you compare them to these incredibly powerful computer simulations called TCAD. If the simulation matches reality, well, then we've cracked the case. And would you look at that? This is our first piece of validation, and it is just stunning. What we're looking at is how a PMOS transistor's performance changes the closer it gets to a diffusion break. The solid orange dots, that's the real data measured from the actual silicon. And the open circles, that's what the computer simulation predicted. I mean, the match is almost perfect. The model is literally predicting reality. Okay, but let's double check, just to be sure. Here's another example. This time we're changing the spacing between the fins inside a PMOS transistor. Again, the blue dots are the real silicon data, and the red circles are from the simulation. And once again, it's an incredible match. This isn't a fluke. This confirms that we really, truly understand the physics going on here. But what about the tricky one, the more complicated NMOS transistor? Well, even here, with that whole tug of war of different stresses going on, the model still works. The blue dots, our silicon measurements, fall right in line with what the simulation predicted. So we can say it with confidence. We know what's happening. The mystery is solved. So when you put it all together, the big takeaway is this. What looked like random, unpredictable chaos is actually a clear physical effect. These local layout effects aren't a mystery anymore. They're a predictable, modelable part of the physics. And that leaves us with a really fascinating final question. Now that we can predict the chaos, can we engineer it? I mean, think about it. This knowledge completely changes the game. It takes what was once a huge problem, a performance killer, and turns it into a known variable, something you can analyze, model, and maybe, just maybe, even engineer on purpose. The next frontier isn't just about avoiding these effects, but maybe even using them to our advantage.